Okay, reflections. So before we get into reflections, I want to go over a rigid transformation. A rigid transformation is a type of transformation that preserves the size, length, shape, lines, and angle measures of a figure. So basically nothing really changes as far as the shape and how big or how small it is. And the side lengths don't increase or decrease, the angle measures don't increase and decrease, they just remain the same. That being said, we can say that the pre-image and image are congruent. So we'll be able to differentiate between the pre-image and the image in just a second. There are three types of rigid transformations, and we're going to look at these three types of rigid transformations: reflection, translation, and rotations, but today we're just going to go over reflections. Okay, so rigid transformations, everything pretty much stays preserved. The size of the shape does not increase or decrease, it stays the same. So what is a reflection? Well, a reflection is often referred to as a flip in a plane. So as you can see here, we see our pre-image being flipped across a line of reflection to create our image. So our pre-image is going to be that which happens before the transformation, before, and the image is going to be that which happens after. We're also going to see that our pre-image has no prime notation while our image does. So we know, or we're able to differentiate between the pre-image and the image because the image contains the prime notation. Okay, any questions so far? Okay, let me go ahead and share my other screen and we can begin. Okay, so a reflection. So in a reflection, all the points of the pre-image are reflected across a line of reflection to produce an image. So there's always going to be a line of reflection where that reflection takes place across, right? So in this instance, this would be our line of reflection. And what it does is it basically takes our pre-image. Again, the pre-image is that which does not contain that prime notation. So the pre-image is flipped across that line of reflection to create a resulting image. Okay? And so that's what we see here. So we represent this reflection using this notation right here. And what this is basically saying is that triangle ABC is mapped to triangle A prime, B prime, and C prime. So these symbols represent prime. And this arrow right here represents maps to. So we read this as triangle ABC maps to triangle A prime, B prime, and C prime. Okay. Okay. So what is the formal definition of reflection? Well, the formal definition is a reflection is a transformation such that the line of reflection, so we have our line of reflection, is the perpendicular bisector of the line segments connecting a point in the pre-image with the corresponding image. So for example, well, first, this is my pre-image, right? Because it doesn't contain that prime notation. And this is my image. So what is it saying? Well, it's saying that the line of reflection is the perpendicular bisector of the line created between my pre-image and my image. So if I were to draw a line between my pre-image and my image, like I see here, the line of reflection would act as the perpendicular bisector, so it would be perpendicular to it at a 90-degree angle, and basically it would cut it into two congruent halves, like this. Okay? And same thing goes from all the points. So if we created a line segment from A to A prime, the line of reflection would be that perpendicular bisector, so it intersects it at 90 degrees, and it also cuts that line segment that we created into two congruent halves. Okay. Another unique thing about reflections that we need to pay attention to is that points located directly on the line of reflection, like C in this example, map back to itself. So it doesn't necessarily move, it just maps back to itself. So that's another key takeaway here. Okay. So the line of reflection is the perpendicular bisector of the different line segments created between the point of the pre-image and the corresponding image. And lastly, any points located on the line of reflection map to itself. Okay. So what does it mean for something to map to something? Well, we'll get into that in a little bit. But the first thing, how come a reflection is a type of rigid transformation? Well, like we discussed, rigid transformations preserve everything having to do with the shape, the lengths of the sides, the angle measures, the types of shapes, etc. So everything is preserved. In reflections, same thing happens. All the segment lengths are preserved. All the angle measures are preserved. So nothing changes. They are congruent to each other from the pre-image to the image. But the only thing that may change is the orientation. For example, here we would have our pre-image. And here we have our image. And what we notice is that the orientation changes a little bit. And what I mean by orientation, well, here's an example. Here we have L, and we can say that L is kind of facing this way towards the line of reflection. Well, the L on this one is facing a totally different way of that line of reflection. So as we can see there, the orientation kind of changes. Another way that we can see that the orientation is changing is say that we have our left side of that image and our right side of that image. We have the left side and the right side. What we'll notice is that in the pre-image, that J is on the closer to the right side, and over here that J is closer to the left side. And so the orientation is changing, but that does not mean that it's not a rigid transformation. Reflections are types of rigid transformation. Okay. So now we're going to get into different reflection rules. So we have different types of reflections. We have reflections across the x-axis, reflections across the y-axis, reflections across y equals x, and reflections across y equals negative x. And depending on the type of reflection we have, our coordinates are mapped to different locations. So basically, whenever the reflection takes place, wherever that coordinate or that vertex maps to will change. So, for example, if we have reflection across the x-axis, we have reflection across this axis right here, okay? The rule for reflection across the x-axis tells us that the x-coordinate remains the same and the y-coordinate is negated. So this would represent my pre-image point, and this would represent my image after the reflection. So what this rule is basically saying is, let's say, I'm going to map it right here, so B prime. Okay. So I'm going to find out where that coordinate maps after reflection across the x-axis. Well, like it says, my x-coordinate remains the same, so I have -1. And my y-coordinate is negated, so it becomes a -5. Basically, negating means just changing the sign. The negation means changing the sign. If it was originally a positive, it'd become a negative. If it was originally a negative, it'd become a positive. So what we see there is here we have our pre-image. And here we have our image. And what we're seeing happen is that here was our original B, and after the reflection across the the x-axis, we get our resulting vertex at where B prime is, okay? And so the importance of this is being able to know where those coordinates map to each other, because say you're given a problem where this is the only information you are given. You're only given information about the pre-image and you're asked to find where the resulting image would be located. Well, what you would have to do is, let's say there's a reflection across the x-axis like we just saw. Well, what you would have to do is apply the rule for that reflection to each of the coordinates. So, like it said keep the x the same and negate the y. So now I have -6 and -6. So my resulting coordinate would be located right here. So this would be my A prime. And basically I would do that for all the different coordinates. And by doing so, I would be able to find out where my image maps after that type of reflection. So it would map right here. Okay, and we're going to see that this changes depending on what type of reflection we have. Okay. So any questions about reflection across the x-axis? Again, the rule is the x-coordinate remains the same and the y-coordinate is negated. Any questions? Okay. Now we're going to look at a reflection across the y-axis. So again, we're mapping our pre-image to its resulting image, and we're doing it about the y-axis. So now we have a different type of reflection that goes about the y-axis. Well, the rule for a reflection across the y-axis is the y remains the same and the x value is negated. So say I want to map k. So I want to map k. K is originally right here at -1 and 3. And now I want to see where it maps after reflection across the y-axis. So it says my y-coordinate remains the same, so 3. And my x-coordinate is negated, so it becomes 1. So it should map to 1 and 3, which we see that it does in fact do that here. Okay? So again, why is this important? Well, say that I'm start only with information about my pre-image, which I see here, and I'm asked to identify where that pre-image maps after reflection across the y-axis. So now I'm going this way. Okay. Well, what was I just told? I was told that my y remains the same, but my x is negated. So now it's going to map to 6 and 6, and so it would map right here. And so what I can see is that depending on the type of reflection I have, the location of where those coordinates map to change, right? I went from being in this area to this area over here. So you can see here that this is where that square would map to after reflection across the y-axis. So that's why it's important to know these mapping rules to be able to determine where the pre-image gets mapped after a specific type of reflection. Okay. So that's the reflection across the y-axis. So does anyone have any questions about reflections across the y-axis? Questions? So far, we've looked at a reflection across the x-axis and a reflection across the y-axis. A reflection across the x-axis tells us that the x remains the same and the y is negated. A reflection across the y-axis tells us that the y remains the same and the x is negated. Right? So those are our mapping rules. Okay. Now we're going to look at a reflection across y equals x, which looks like the line that we see here. But whenever we have a reflection across y equals x, the x and y coordinates will be switched. So again, say that I start with D in my pre-image right here. D is located at 2 and -4. So say I want to find out where that maps to after reflection across y equals x. So D prime. And I'm just going to do what it says to do there. The x and y coordinates are switched. So this one becomes -4 and this one becomes 2. So -4 and 2, which we can see is correct. Okay. Now again, why is this important? Well, let's go back to our original image. Okay. Again, say we start with the blue square, and I want to find what the reflection of y across y equals x. So say I want to reflect blue across y equals x. Okay. So I'm going to look at my A, this one right here, and do what it says. Switch the x and y coordinates, so it becomes 6 and -6. What does that mean? That means my A will map right here. going to try to show you where it will map to. Okay. And so that would be, this would be my resulting image after reflection across y equals x, right? So I need to know those mapping rules in order to be able to map my squares where they need to be, or any of my figures where they need to be after a specific type of reflection. Okay, so the rule for this one is a reflection across y equals x means that we switch the x and y coordinates. Okay, and lastly, we have a rule for reflection across y equals negative x, which looks like this. Whenever we have a reflection across y equals negative x, we switch the x and y coordinates and then negate them. So let's look at our example. We'll look at A in our pre-image is located at -4 and 5. -4 and -5. So I want to map that. What am I going to do? I'm going to switch my coordinates first. So -5, -4, and then I'm going to negate them. So I'm going to change the sign. So now I should map at 5 and 4. 5 and 4, so this would be my new A. Okay. So the rule for this one, when I have a reflection of y equals -x, I first switch the x and y coordinates and then negate them. Okay. So does anyone have any questions about what I'm doing here or any of these different mapping rules? Reflection across the x-axis, reflection across the y, reflection across y equals x, or reflection across y equals -x. So basically what I'm doing is I'm able to use these mapping rules to find out where my coordinate will map to from my pre-image to my image. Pre meaning before the transformation like we discussed before, and our image being that image after that specific transformation, or in this instance, it's a reflection, okay? So why is this also important? Well, sometimes we may be asked to determine the pre-image. So that means we actually have to work backwards. If we're determining the pre-image, that which happens before the reflection, pre meaning before, we need to work backwards. So say that we know that rectangle Q prime, R prime, S prime, and T prime was created using the following rule. This rule tells me that I have a reflection across y equals -x. What do I know about reflections across y equals -x? Well, I know the x and y coordinates were switched, and they were both negated. So first they were switched, and then they were negated. Right? That's what I know about this mapping rule. Okay. So that being said, am I able to find my pre-image? Well, yes, you can find your pre-image by working backwards. So that means that first we will negate and then we will switch. So here are locations for our pre-image, the coordinates of the pre-image, or the vertices of the pre-image. This one is at -2 and 4. This one is at 4 and 4. This one is at 4 and 2. And then we'll discuss this one a little bit in just a second, but this is at -2 and 2, okay? So basically we want to work backwards to find our pre-image. That means first thing we want to do, like I said, is negate. So our positives become negatives, our negatives become positive. So first I switch. I'm switching. Oops. Let me show you. To negative. First switch. Okay, so first thing I do is switch, and then I go and negate. So if this is a positive, it becomes a negative. If this is a negative, it becomes a positive. These become negatives. These become negatives. Okay? So now I have switched, and so I'm able to find the coordinates of my pre-image. 2, -4, -4, -2, -4. Okay, so the first thing I did was switch them. You saw that, and then we negate them. So we changed the sign. And so let's see if this is true. Is our Q originally located at -4 and 2? Yes, it is right there. Let me use a different color. Okay. Is our R originally located at -4 and -4? Yes, it is right there. Is our S originally located at -2, -4? Yes, it is right there. So what about my T? Well, like we discussed before, T is located directly on the line of reflection. And because it is located directly on the line of reflection, it will map back to itself. Right? That's what we discussed. Right here, right? Any pre-image points that lie on the line of reflection map to itself. So that's why we don't need to find the new coordinates for T. Okay? However, if we wanted to, you would see that it actually just maps back to itself. So that I know T here is at -2 and 2. Right, and I want to do the same thing. I'm going to work backwards. So switch it to -2 and then negate it. Well, what do you notice there? It just maps directly back to itself. Okay. Any questions about this? So basically, if we need to find the pre-image, we work backwards. Okay. Any questions or concerns? And again, we'll work through some practice problems because this does take some practice. So what did we basically go over today? Well, we learned that a reflection is often referred to as a flip in a plane. And what we're looking to do is start with the original coordinates and be able to find the resulting image. So we start with our pre-image coordinates, that before the transformation, and try to find the coordinates of our resulting image after the transformation, which is the reflection. Okay? And the way we do that is we use our different reflection rules. So we have a specific rule for reflection across the x-axis, a specific rule for reflection across y-axis, a specific rule for reflection across y equals x, and a specific rule for y equals -x. And basically, we just follow those rules in order to change our original coordinates. Okay? Any questions so far? And we'll go over some practice problems tomorrow. Okay? All right. Any questions? Okay. If there's no other questions, I will see you guys tomorrow for some practice problems, and then you can work on independent practice. So I'll see you guys tomorrow. Bye, guys.